So we just calculated the electric field that was induced inside a solenoid. And recall that we drew a picture, an overhead view of the solenoid, in which our magnetic field was directed like that. And we chose our Faradayan loop on the inside of a radius r. And when we calculated the electric field, we found that the electric field was equal to minus mu naught n di dt times r over 2. And now we want to think about the meaning of the sign. Remember, we chose n hat right-hand rule this way, and we chose a circulation direction like that. And in this problem, we had that di dt was positive. And so what we see here is that the current was increasing, and we have a negative sign. So this quantity is less than 0. Now, what does that tell us? Well, whenever you calculate the electric field, and you've chosen a reference frame, and in this case, our coordinate system corresponds to the direction for positive unit normal, and that corresponds with the circulation direction. They're consistent. And now, when you get a negative sign, it means that the induced electric field is opposite the circulation direction. If I had solved this problem, so for di dt positive, and let's just make that positive, E was negative, and it means that E points opposite the circulation direction. Now, I could have done the same problem in which I decreased the current in the solenoid, and then a negative negative would give me a positive electric field. And in this case, I'll just draw that picture again. We were calculating the induced electric field here, circulation direction, unit normal, consistent. Then, in this case, with di dt negative, the electric field is positive, and that means that the induced electric field points like that, in the direction of the circulation direction. And that's how our choice of reference frame for the surface integral and the line integral enable us to determine the direction of E inside the solenoid.